a WEM stroke Watkins ER40 replaced, they came out the early 70s to replace the valve amps. Even in those days, solid state was the way everyone was going. Valves were supposed to be out, solid state was in. So this replaced a similar looking amp. It's available in more powerful ones as well. Still had the same looking construction as the little valve amps they used to make. It was sort of a cheapish case, fairly cheap sort of front panel. This one lost the knob. It's pretty good condition. It's got a treble boost on both two channels. When you first see it, you might think it's a valve amp. It's got some these grills were used on the valve amps, like let the air in. It's got this aperture in the back for changing the voltage, and some fuses. Still, you might think it's valve. Look at the side now. This one's got the original bulging connector, which got the lead here, and some outputs for the speakers, 6, 12, 12. Still, you might think it's a valve amp. It doesn't say, as far as I know, it doesn't say solid state anywhere on it. No. So, anyway, this one's pretty good condition. I think we'll take it apart, look inside, just have a look around before test it, see if it's working. There are 4 sort of like wood screws holding the front panel on to each side, and on the back also there are these really long bolts. 4 of them go into the back, which you can unscrew. So once you've taken them out, the front panel just folds down for easy access, and then you can see inside as well. Some light on the inside. They've obviously gone into this to make this ease of manufacture, quick to manufacture, getting away with all that hand wiring on the valves and everything, to speed up production, cut costs. So we've got a circuit board with all the components on, and this circuit board has got a plug and sockets now, so this can be removed. You can see all the components on here. There's a bit of corrosion. Then on the back is the power section. You've got a really big transformer. You've got the speaker sockets, which are just wired all in parallel, and they've got spade connectors on them as well. The bulging plug has got spade connectors for the mains. 2 big capacitors, and this would be one of the power transistors, and there's another one over there. Looks like there's possibly only 2 power transistors running the whole thing. Now I've undone this, so this is loose now and can be taken out. It's just a folded piece of steel by the looks of it. Some corrosion from the years. Trying to work out the date. These big capacitors sometimes have the date on them, or a code which you can work out what the date is, so we'll have a look at that as well. That'll give you an idea after the date when it would have been made. Otherwise it's just a simple wooden case. These can be cleaned up with switch cleaner. I check the transistors sometimes blow, but I don't see why they would have. They're silicon transistors, not germanium, so they're going to be fairly reliable over the years. I pop the power supply. It probably comes out this way, or perhaps the other way. I'll take these connectors off and get it out. Now, unplug the front panel. It makes it very easy to service. You can take it out. This bulb, I don't know if it's original, been replaced. Anyway, looks like it's been replaced. You can take that off. 2 plugs, and set that aside. And then this obviously slides out from the front. The back is closed in. The back panel doesn't come off the wood panel, and there's enough bit of slack on the wire, so you don't even need to unplug it. Got the two transistors. They're part number 40363. I looked them up. They are 15 amps each, 70 up to 70 volts, 110 volts, 220, 250. Fuses, power transistor, transformer, some form of heat sinking, because silicon transistors in amps can run hot. So just have a look this side. Not many components, just some little driver transistors in heat sinks wrapped around them. They probably get hot, so they've done that. A diode, power supply diodes, capacitor on there. A diode here. Just a few basic components. Quite easy to service. They made it quite easy, though I'm not sure what can go wrong. The transistors can go. And possibly these capacitors will wear out, but everything else, there's not much in here. I'll try and get a circuit diagram, and I'll take one of these capacitors off, see if there's a date code on it. Couldn't really work out the date code from the capacitors. It's not really that clear. But the bridge diode down here, it's got 71 on it. I think that's the year of manufacture. So after 1971, I would guess. Nothing else I can find. That's the date code. The circuit diagrams were available online, and it's a very simple circuit. One thing you can do with the power section is the output to the speaker is between the rail halfway, and it says here about 29 volts, around to 29, and you can adjust that if it's not right halfway with this potentiometer down here, which is down in there, and you just turn it while measuring it. This piece of metalwork here was normally was covering that. It's obviously been serviced at some time, and they've bent this up, physically bent it up and just left it up, because when it's down it's probably difficult to turn that. Everything else looks okay. I can measure the voltages. The preamp is very simple indeed. There's two channels identical, and then it's got an input. It's only very low resistance input compared to a valve amp. If you plug a guitar in, it probably you should really have a buffer, because there's loads of guitar down a lot if you just plug the guitar straight in. It's got 10k. Normally one in the other socket, it cuts the signal in half, so I don't know what the point of that is really. Not much use. Transistors, BC109s were one of the better ones at the time. Were supposed to be low noise, high gain. It's a very simple circuit. Pop for volume. There's a treble cut to earth, and there's a bypass here which normally only lets the treble through, and if you turn this up, lets the bass through. Pretty simple. And then both the inputs are joined together down just onto this transistor that goes off into these sockets, and that's it really. Not much to it. There's a bridge rectifier for the mains. So I'm going to change the socket, the main socket in the side, the bulging one, probably to an IEC modern one, so people can use a modern kettle lead, mains lead, rather than the bulging plugs are really expensive. So it's just a matter of checking the voltages, power it up, and then after I clean the pots and that as well. Testing the voltages and setting the output voltage to the speaker to half a rail. Let's just turn up the mains, which should be 44 volts, and we turn it up to 235. Let's advance that. That's the AC. 235, it's spot on. 44 volts, which should be. 59 volts on the rectified position on the circuit board. They say 54, but that's there's no load on it at the moment. And they say 29 volts, no load. There's 34 volts. So put the screwdriver in the adjuster, adjust it one way or the other, just this way. 30 volts, about 29 volts. It's basically half the rail voltage, which is what it should be. So that's rails 59, so that's perfect now, according half point there, which will go after the speaker, so that the signal can swing from one point to the other. Everything else seems to be fine, so it's just a matter of checking the preamp. Looks fine. Pot's probably going to need cleaning, they're probably scratchy. Cleaned all the potentiometers and switches with some cleaner, just winding them backwards and forwards and switching them backwards and forwards. One thing you notice on here, the transistors are BC149Cs. You can't read it, but it is written on there. The original drawing said BC109s, but BC149Cs are basically the same transistors, high gain. C is the high gain version. The low noise, the BC109s were low noise too. Another thing that is slightly different is they've got this is a slave output. It's wired directly to the point here where it comes off this transistor that goes off to the power amp, and they've just connected it directly to the socket. You could slave in, but I think it's for out. Another thing is they haven't earthed the front panel. If you check out the front panel with this meter, you see that's the front panel connection, short. But if you connect it to any of the earth connections, it's showing a slight resistance only. I don't know why they haven't done that, because it would help get rid of any noise. I don't know whether they hope to get a connection through the pots and it's just got corroded. So it's easy to do. You just you put a small tag on one of these mounting points and just connect it to an earth wire just across. I've got a tag somewhere. Another thing is the bulging plug round are pretty rare these days and very expensive if you need to buy one, a lead for it. You can get the modern one like this, takes a kettle lead, IEC. You can get it this shape, and it should go in. There's two mounting screws, it should fit in place. Also, they still come with the same push-on connectors on the back, so I'm going to put that in. Otherwise, I think everything's looking good. Do a quick check with the signal generator, which I've got over there. Plug it into one of the channels. There's no noise from the front panel, which is now earthed. Stick it in. Check the tone controls. That's about 400 Hertz. Go down. That's about 40 Hertz actually. It's probably a bit too low. Take it up to 100 Hertz. Bass works. 1 kilohertz. Try the treble boost. Oh, a bit noisy. Definitely put treble up. Yeah, treble boost is working. Let's increase the frequency a bit. It's nearly 5 kilohertz. Oh yeah, treble boost definitely works at 5 kilohertz. Try the other input. Lower volume, that's the one that cuts it in half. Let's try the other one. Yeah, it definitely works. Lower the 1 kilohertz. Tone controls don't have much effect at 1 kilohertz. Let's lower the frequency a bit. Bass. Well, the bass control definitely works at the end of the throw. So all the controls are working. So say that one. So yeah, it's just half volume. Just got to put the rest of the screws in the front panel. Shame about the thing missing there. And I can put some guitar or something through it now and connect it up. We could use it to test a speaker. Measuring the power output of this WEM ER40. How to do it? Well, I've drawn up a graph here which shows different resistive or speaker loads versus the RMS voltage across measured across them, which will give you the watts output. It's just a simple formula, but I drew a graph anyway. Now on the resistive load over here, I can set the load at 4, 8, 12 or 16 ohms. I can set the input voltage, measures the input current as well, so I can keep that steady. And then on the scope, you can watch the sine wave. The red's the input frequency, and the yellow one is measured on the load, so you can see when it starts clipping. Now on here it measures RMS across the speaker. So for instance, if it was going to get 40 watts across a 12 ohm load, you'd expect the voltage to be about 22 volts on that meter. So what we're going to do, I've got the 12 ohm load. Now this can take, according to this side, it says you've got to put, you can have a 12 ohm or a 6 ohm load. Now 6 ohm would draw the most current. That would be pretty heavy. I have a 4 or 8. I don't actually have 6 ohms set in. To test it first, 12 ohms, because it's voltage limited from the power supply, it tries to push as much current through. Well, on the higher ohm resistance, it won't be able to push as much current, so we don't want to burn it out straight away. When you put a low load, it draws much more current and should give more power, but the load on the power supply and all the components will be at absolute maximum. And remember, this is a musical amplifier. It's not supposed to be delivering a constant power output, which it's meant to be power output be up and down as you play the music, so it's not such a big stress. So we don't want to hold it on the maximum power for long. Anyway, all that said, I should test it about 1 kilohertz, so I'll just turn up this frequency to about 1k. say there. I've got a little monitor speaker which I'll turn down a bit, just so you can hear also whether it's going really weird sounding. So as you can see, there's a bit of a slight phase shift, which you would expect anyway through an amp. Let's turn that speaker off, it's too loud. So I'm going to turn up the input at 1 kilohertz. I've got the controls, tone controls on maximum. We can check the operation of the. Oh, got a bad connection somewhere. Check the operation of these boost switches anyway. So I've turned it up. It's now 12 volts. It's showing. That's here, about 12 volts on the 12 ohm load. That's about just under 20 watts at the moment. Let's turn up a bit more and watch the waveform there peaking out. Now that should be equal top and bottom because I set the power supply halfway, which is correct. So there is the maximum before distortion. 15 volts, 12 ohms, it's about 18 watts. Let's turn this back down a bit. 18 watts. So let's put it on 8 ohms, see how it manages that. Up there. Going 14 volts. I'll turn it down a bit. 14 volts across 8 ohms this time. So 14 volts plus 8 ohms, which is this one. It's getting on for 25 watts. 25 watts. It's not bad. Now I don't have a 6 ohm set in. I can put it on 4, which is going to be quite a. I'll try 4. We don't want to blow it. So what's the voltage? I don't want to put the voltage above about 10. It's 10 now, just peaking out there at about 11. Let's turn it down. So 11 volts at 4 ohms. Go along here. 4 ohms. It's about there. It's about 28 watts. So not too bad. 28 watts at 1 kilohertz, not 40 obviously, but that's quite powerful, quite loud, and much more powerful than the previous valve ones that they made, the EL84s, which were only rated about 15. They called them a 17 watt in the end. So changing to silicon transistors has given them quite a boost in power output. Let's just turn that to show the waveform again. That's the meter, 11. That's on the 4 ohm load up there. Set right down at 4. Could test it also the frequency bass. It'd probably suffer at the bass more than the treble, but that's what you would expect. I mean, we can reduce the frequency down to, say, something quite low, 50 hertz. No, let's put it down to about 100 hertz. Let's just change that. 70 hertz. Let's put the bass up. Now that's going to be quite a struggle at 70 Hertz there. It's beginning to go wrong about there. What's that? Pretty impressive. Still 11 volts at 70 Hertz, which is same as the as at 1 kilohertz. 11 volts here, up here, getting on for 30 watts. That's impressive. Shows that the big output capacitor that they're using is still working well to pass the signal. So that's the test on the WEM. It's all working good, and a nice little powerful amp. What about distortion on this amp? Well, valve amps, we know, get a lot of their characteristic distortion from the valves and the input stage, as well as in the power stage. What about transistors? Well, they tend to be pretty linear until they shut off, unlike valves. Now looking at the circuit, the volume control is here, right after the first amplifier stage, it's a transistor. So any distortion from a large input signal is going to happen on this transistor. To try and measure distortion after that, going through the circuit, we could put a signal, a scope or something on the slave here and have a look, which would be this part before it goes to the power section. Anyway, I can show you the distortion just from this transistor here, just by turning up the gain with the volume control right down. I've got 1 kilohertz going in, that's, and the yellow signal is what's on the speaker. So what I can do here is just turn up the gain of the signal going in, and you can see it's let's just move the red one down a bit. That's, you can see it's distorting just one part of the signal, the top part. Now if we change the turn the treble up, let's really change the distortion to spiky now, and bottom. Turn the treble back down. Let's try some treble boost. Just peaking, just cutting the top off. So it's got distortion, but sort of asymmetric. Just turn the treble up. It's more linear if you've got the treble right up. That's at 1 kilohertz. Let's do 100 hertz. And try the bass control. Turn it up. Or 100 hertz. You've got a really weird signal. Let's turn the bass up a bit, or turn it down, turn it up. Well, when the bass is down, it's really odd shape. Turn the bass fully up, and you can see it's similar to the treble one. Now it's just distorting one side rather than the other side. So I would say that was caused by this this transistor not having quite the right symmetrical voltage on the bass. If you adjusted that voltage, you could get symmetrical, but who knows what sort of sound you're looking for by overloading. But transistor amps are not generally used for making an overloaded sound unless you go really, really high on the input distortion, like John Lennon Revolution, was it? We just overloaded the input just by a massive amount. Anyway, it is a type of distortion, but different probably from a valve. The circuit's pretty straightforward. I mean, it just amplifies, and then you've got just some frequency shaping around this valve, some bypass, treble cut, and then a bit more amplification to drive off to the power section. It's a very simple circuit, really. Just a quick look at this point on the output of the preamp to the power amp. You can connect it there, the red probe, the red signal on there, just showing that it's not the preamp that is distorting when it hits maximum power. It's actually the power section, which is the yellow probe on the speaker. If I just turn up the volume of the input a bit, the yellow is distorting, that's the speaker, that's due to the power supply. And you can see the red signal, which is going into the power section, measured here on the slave output, is not distorted. So it's actually the power supply that is beginning to distort at maximum signal, not the preamp. Now just show you the current as I turn it up, how much current it's drawing. You can work out the input power as well. So turn up the voltage. This is at 70 Hertz. It's just peaking out there, about getting on for 30 watts. It's just drawing about 0.3 of an amp. So it's quite efficient, unlike a valve amp, which uses a lot of power as heat. Quick check to see how it works with the guitar. Just plugging the guitar straight in. One of the channels, both of the channels are the same. That's quite bassy. I've got the controls. Let's have them down first. Put the guitar on the treble pickup. Turn on treble boost. That's pretty effective. Try treble control. It's got some range. Now the treble boost. It's very bright. Turn that off. Try the bass. At the end of the treble, it really brings the bass up a lot. So put some treble back on. Pretty clean sound. Put treble boost on. Sounds a lot better with the treble boost on. It's a treble pickup and a full bass pickup. Yeah, it gives it a much brighter sound, a fuller sound with all the controls up full, as you'd expect. The volume's pretty low. I can check out the power output in a minute. Pretty loud sound. I think it sounds pretty powerful. Nice clean sound. That was on the bass pickup. On the treble pickup, pretty much cuts through a lot. So it's a very clean, powerful bass to treble sound. Not like a valve. There's no real distortion, so it lets the guitar sound come through very well. Treble's a bit in your ear, try and in between. Pretty good sound actually. I think you could work with that. So both channels obviously are the same. I'm going to check the power output. It's called an ER40. I don't know if they're pretending it was 40 watts, but I doubt if it goes that high. So it's got a nice solid sound. That's a guitar just plugged straight in. It's quite impressive really, it doesn't sound weedy at all.